Hello there, and welcome to the Sleepy Space Channel. Tonight, we are drifting softly through the catalogue of impossible worlds, the planets the galaxy has made at the very edges of what physics allows. The hottest worlds, glowing with vaporized iron in skies that never see night. The coldest, drifting through the dark on orbits so wide that one of their years is longer than human history. Planets where the rain is made of glass, planets less dense than cork, planets older than the Milky Way's spiral arms. Each one is real. Each one is turning patiently in its own corner of the galaxy, far enough away that nothing it does can disturb us. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. There is a quiet truth that the night sky carries without ever quite saying. Every small point of light you can see, and every fainter one you cannot, is almost certainly accompanied by at least one planet. The stars are not lonely. The galaxy is full of worlds, in numbers that go past the ordinary words for numbers. Over the past few decades, astronomers have catalogued more than 6,000 of them by name and by orbit, and behind that named catalogue, there is a much larger population, tens of thousands of candidates waiting in the queue, and behind those, hundreds of billions more in the Milky Way alone, most of which we will never see directly. Tonight, we are going to walk softly through the edges of that catalogue. Not all of it. The strangest ones. The record holders. The worlds where one quality has been pushed to its limit, and the catalogue has produced something extreme. The hottest. The coldest. The densest and the lightest, the oldest and the youngest, the closest and the most distant, the loneliest and the most crowded, the brightest and the darkest, the most stretched and the most still. Each one is real, somewhere out there in the dark, turning quietly under the same physical laws that turn the Earth. The catalogue grows in a soft way, year by year. A small star somewhere far away dims very slightly, and astronomers notice the dimming, and they watch, and the dimming repeats on a schedule. The schedule tells them a planet is passing in front of that star. The depth of the dimming tells them the planet's size. Long, patient observation tells them the planet's mass, the shape of its orbit, sometimes even what its atmosphere is made of. Each record we are going to visit was found that way, patiently, in small dips of light. None of it was hurried. The galaxy has been holding these worlds for billions of years. We are only now beginning to notice them. You can let your breathing settle as we begin. There is no hurry here, and nothing to fear. Every planet we will visit is held safely behind dozens, hundreds, or thousands of light-years of dark. Many of them are so far away that the light leaving their suns now will not reach Earth in any human lifetime. They are not coming toward us, and we are not going to them. We are only going to look softly through the catalogue, one record at a time, and let the strangeness of the universe accumulate gently in the room around us. The first thing to know about the records in this catalogue is that they are not freaks of nature. They are not accidents or oddities. They are the visible edges of the same physical laws that built the Earth. A planet hot enough to vaporize iron is not strange because the rules are different there. It is strange because the same rules, dialed differently, produce that kind of world. Gravity, radiation, chemistry, conservation of motion. 4 or 5 simple ideas, repeated hundreds of billions of times, with the dials at different settings. The records are how we see what the settings are allowed to be. Some of the planets we are about to meet are smaller than our moon. Some are larger than Jupiter but lighter than cork. Some orbit their suns every 2 hours. Some take more than 1 million years to complete a single year. Some are so old they formed in a universe that did not yet have most of the heavy elements that build worlds today. Some are so young that they are still gathering their material from the disk around their parent star, growing visibly under direct imaging. Some have suns. Some have several suns. Some have no sun at all. Some have rings. Some have tails. Some have rain made of glass, or of iron, or of liquid water in air colder than Antarctic winter. You do not need to remember any of them. The names will pass through gently. What we are after is the soft sense of the catalogue's shape, the feeling that the galaxy contains a much wider range of worlds than the one we live on, and that all of it is held quietly in the dark, far enough away that it cannot disturb you. The galaxy is roomy, not crowded. The records are quiet, not loud. The universe carries its strangest creations softly. Let us begin where the records of heat begin. A small note before we begin. The names of these planets are often awkward long strings of letters and numbers that say nothing pleasant when spoken aloud. Kelt, 9b. PSRB, 1257 plus 12d. OGLE2, 005, BLG 390LB. The names are simply the survey designations from the instruments that found them: the Kilodegree Extremely Little Telescope, the Optical Gravitational Lensing Experiment, the radio observations that detect pulsars. The names will pass through the night gently. What matters is the worlds themselves, not the labels. Each one is a real arrangement of atoms held together by gravity, somewhere out there in the dark. The labels are only the rope we've thrown to them across the distance. The current record holder for the hottest known planet outside our solar system is an enormous, slightly bloated gas giant, catalogued as Kelt, 9b. It orbits a young, fast-spinning blue-white star about 650 light-years away, in the direction of the constellation Cygnus. The planet's year, the time it takes to complete a single orbit, lasts only 36 hours. Its dayside temperature reaches roughly 7,800 degrees Fahrenheit, or about 4,300 Kelvin. That is hotter than the surface of an average small red star. That is hotter than the metal in the heart of a steel furnace. That is hot enough that the molecules astronomers expect to find in giant planet atmospheres, water vapor, methane, ammonia, are torn apart on the dayside, leaving behind a thin, glowing soup of atomic and ionized metals. Iron, titanium, sodium, magnesium. The kind of vapor normally found inside stars, not around them. If you could stand on a small moon near Kelt, 9b, which you cannot, because no such moon could survive there, and look at the planet's dayside, you would not see clouds. You would see a glowing, banded sky of metal vapor, with the host star filling nearly a third of the visible horizon. The day would never end, because the planet is tidally locked. One side faces its sun forever, the other faces forever into the dark. On the day side, the atmosphere is slowly evaporating, the topmost layers being pushed outward into space by the relentless light. A thin, trailing tail of hot gas follows the planet around its orbit, fading slowly into the night behind it. The planet is, quietly, becoming smaller with every year that passes. The number that makes Kelt, 9b extreme, is not its mass or its size. It is large, but not unusually so, slightly larger than Jupiter, about 3 Jupiter masses. The number that makes it extreme is its temperature. It sits closer to its Sun than Mercury sits to ours, and its Sun is much, much hotter than our own. The combination puts more energy onto every square mile of its surface than any other planet in the catalogue. The science of how such a world's atmosphere even holds together at that heat is one of the open puzzles of the catalogue. The atmosphere we see today is being slowly cooked away. The planet that remains in a few 100 million years will be smaller, denser, and quieter. To stand at any distance from Kelt, 9b would be to feel its sun before you saw it. The star is itself a record in its own right. A young, hot, blue-white object, spinning so fast that its equator bulges outward, slightly flattening the disk. The planet feels the difference between the equator and the poles in its own atmosphere. One side of its orbit catches slightly more of the star's harshest light than the other. The atmosphere's chemistry shifts in response. The world is, in a quiet sense, not a single steady environment, but a slow oscillation between two very similar fires. Beneath the hot upper atmosphere, the deeper layers of Kelt, 9b, are still, by ordinary standards, very hot, but they are not the 4,000-degree furnaces of the day side. There, the chemistry returns to something more like an ordinary hot Jupiter hydrogen and helium, with traces of water vapor and methane, all of it kept just below the dissociation temperatures of the topmost layers. The planet is a layered onion of temperature, with the most extreme conditions at the top and a quieter, more familiar interior below. Models suggest that the bottom of the atmosphere is something a less extreme catalogue would simply have called a hot Jupiter. The night side of Kelt, 9b, is a different world entirely. There, the temperature is still around 2000 Kelvin, hotter than the surface of the average red dwarf, hotter than the day side of most ordinary hot Jupiters. But it is, by Kelt 9b standards, cool. The same metals that vaporize on the day side cool and recondense on the night side, forming a slow circulation pattern that astronomers can trace by carefully timing the planet's spectrum at different points in its orbit. The night side glows softly in the infrared. The whole planet is a kind of slow, standing wave of heat, perpetually being driven from one side to the other and back again, never quite reaching equilibrium because the day side is always being refreshed by new starlight. The same physics atmospheric circulation under intense one-sided heating happens on all the ultra-hot Jupiters in the catalogue, with different intensities and chemistries. In each case, the day side is the source of energy, the night side is the slow drain, and the winds between the two are responsible for whatever weather the planet shows. The strongest of those winds, on the most extreme worlds, reach speeds of 3 or 4 miles per second supersonic in the planet's own atmosphere. The slowest, on cooler worlds, are gentler, more like terrestrial trade winds. The records of heat are also, in this softer sense, records of wind. The hotter the day side, the stronger the wind, the more dramatic the chemistry it can carry between the two halves of the planet. Just below Kelt, 9b on the heat scale, sits another giant, slightly cooler, but holding a different record of its own TOI, 2109b. This is a hot Jupiter on the shortest known year for any gas giant in the catalogue. Its orbit lasts only about 16 hours. To complete a year, the planet falls almost the full circuit of its orbit in a single Earth night. Its day side reaches around 3,500 degrees Kelvin, perhaps 6,000 degrees Fahrenheit, and its surface, were there one, would never see darkness. The planet sits so close to its sun that the star's gravity is slowly dragging it inward. Over the next 10 million years or so, the planet will spiral in and be torn apart and absorbed. 1 million human civilizations could rise and fall in the time it has left, but on the timescale of the galaxy, it is already falling. The script can hold this gently. A giant world, very slowly, falling into its own light. Down on the rocky world side of the catalogue, the heat records are held by a small family of so-called lava worlds. The clearest record holder among rocky planets is K2-141b. It is only slightly larger than Earth, about 1.5 Earth radii, about 5 Earth masses, and it sits in an orbit so close to its Sun that its year lasts only 7 Earth hours. Its day side is permanently molten. Models suggest that on the lit side, the surface is not solid rock, but actual oceans of liquid magma stretching for thousands of miles. The temperature of those oceans is around 3,400 degrees Fahrenheit, hot enough that the rock itself vaporizes from the surface and rises as a thin atmosphere of silicon monoxide, sodium, and potassium gas. The temperature on the night side, by contrast, is below -300 Fahrenheit. The two sides of the planet span a temperature gap that crosses the boiling and freezing points of nearly every common substance, all at once. Between the day side and the night side, there is a thin strip, what astronomers call the terminator, where the temperature drops from molten to frozen across only a few hundred miles of distance. The wind in that strip is intense and one-directional, blowing from the day side toward the night side, dragging vaporized rock with it. When the vapor reaches the cooler night side, it condenses. The rock cools. The droplets fall. On K2-141b, the rain is made of rock. The drops fall along the terminator, slowly, in a soft cycle that has been running for billions of years. You can imagine it, very gently, if you like, a thin line of falling stone along the world's edge, the only weather on a world otherwise too hot and too cold for any other kind. Closer to home in size, but pushed in the same direction by heat, sits the super-Earth 55 Cancri, sometimes called Janssen, after the early astronomer who unknowingly observed the planet's host star. Its mass is about 8 times the mass of Earth. Its radius is about twice ours. Its year lasts 18 hours, and its dayside temperature reaches around 4,400 degrees Fahrenheit. The planet's interior may be unusually rich in carbon. Its host star has more carbon than oxygen, and some models suggest the planet's mantle could include layers of compressed diamond. Whether or not the diamond is real, the dayside is almost certainly partly covered in molten rock. 55. Cancri E also has a mystery the catalogue has not yet explained. Observations across many years show that the hottest spot on the planet is not at the substellar point, not directly under the Sun, but offset by an unsteady amount, as if a thin, slow atmosphere is dragging the heat sideways. The brightness of the planet's dayside has varied by a factor of several across different epochs of observation, suggesting that the atmosphere or surface is changing on timescales we can almost watch. The leading guesses are volcanic outgassing, tidal heating from the gravitational pull of its neighbors, or some kind of thin, transient atmosphere of vaporized material. None of the guesses is fully confirmed. The planet is one of the closest hot super-Earths to Earth, only about 40 light-years away, and over the coming decades, it will probably tell us a little more about itself. For now, it is held softly in the catalogue as the hottest super-Earth, the world whose hotspot wanders. You can let the heat fade now. The catalogue also holds the other end of the scale, and the worlds we are turning toward next are very, very cold. The coldest confirmed exoplanet is a small, icy super-Earth, catalogued as OGLE 2005 BLG390LB. It orbits a faint red dwarf star, roughly 20,000 light-years away, in the direction of the galactic center. The planet's mass is about 5.5 Earth masses. Its surface temperature is estimated at roughly -370 degrees Fahrenheit, about 50 Kelvin. That is colder than the surface of Pluto. That is only a few dozen degrees above the temperature of the cosmic microwave background, the residual warmth of the universe itself, the faint heat left over from the early hot moments of cosmic history. There is almost no warmth available on this world. Its host star is small and dim, and the planet orbits far enough out that the light arriving on its surface is very faint. The way this planet was found is itself part of why it is extreme. It was not detected by transit or by radial velocity, the two most common methods. It was detected by gravitational microlensing, a method that depends on a precise, brief alignment of stars. The planet's host star drifted, very slowly, across the line of sight of a more distant background star, and for a few weeks, the host star's gravity bent the background star's light into a small, magnified peak. The peak's exact shape carried a tiny additional ripple, a faint extra bend in the light that lasted only a few hours, caused by the planet's gravity adding its own small contribution to the lens. That ripple is the entire record we have of OGLE 2005, BLG 390LB. The planet has not been seen since. The alignment that revealed it will not repeat for thousands of years. We know the world exists. We will not see it again in any human lifetime. That is a gentle thing to hold, if you want to. A world found in a single brief alignment of light, never to be seen again, and somewhere out there in the dark, still turning on its long cold orbit, doing what it has always done. A different kind of cold record belongs to a free-floating object called WISE 0855 to 0714. This one is unusually close, only about 7.5 light-years from Earth, closer than every named star except for our own immediate neighbors. Whether it counts as a planet or as a brown dwarf depends on where you draw the boundary. Its mass is somewhere between 3 and 10 times the mass of Jupiter, which puts it on the soft borderline. What is unambiguous is its temperature, somewhere between -8 and -30 degrees Fahrenheit. That is colder than nearly any object we have ever directly characterized in space. Its atmosphere is cold enough that water vapor condenses there into water clouds. Astronomers studying its infrared spectrum have detected the signatures of methane, ammonia, and water, and they believe that on this small, dim world, far from any sun, water clouds form, drift, and rain. You can imagine that softly, if you like, a world drifting alone through the local stellar neighborhood, far enough from any star that no daylight reaches it, with skies full of cold water clouds and slow rain falling through cold, thin air. The rain is liquid water. It falls into deeper, colder layers. Somewhere in its atmosphere, the same molecules that make rain on Earth are doing the same gentle work, but in air colder than Antarctica. The wider implication of WISE 0855 to 0714 is that the boundary between the smallest stars, the largest planets, and the cold drifting in between objects is a soft one. The galaxy makes objects across the entire mass range, and the catalogue is only beginning to fill in the population of cold drifters near the sunday. There may be many more, possibly dozens or hundreds, sitting in our local stellar neighborhood, invisible because they emit so little light. The cold population is everywhere. The warm population is simply easier to see. The catalogue, in this sense, is a portrait of where light is, more than where worlds are. The pulsar planets carry a different kind of cold in them. Their host star is a neutron star, an object whose entire mass, a little more than the Sun's, is compressed into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh as much as a small mountain. The neutron star's surface is a thin, solid crust of crushed iron, beneath which sits a sea of degenerate neutrons. The whole object spins many times per second, sweeping its narrow radiation beams around like a slow lighthouse. The planets feel the sweep more than the warmth. From their surfaces, the sky would be a quiet, dark canvas, with the pulsar appearing as a faint, fast flickering point, one flash per rotation of the neutron star, alongside the ordinary stars of the galaxy. Some of the coldest planets in the entire catalogue orbit pulsars, neutron stars left behind by ancient supernovae. The first 3 exoplanets ever confirmed by anyone were the 3 planets orbiting PSR-B 1257 plus 12, a small, fast-spinning neutron star about 2,300 light-years away. These planets were discovered slightly before any planet around a normal star. They were the first confirmed exoplanets in history. They are also, as it turns out, among the coldest. A pulsar radiates almost all its energy in narrow beams of high-energy particles and light, rather than as the steady, diffuse warmth a star gives off. The 3 planets receive very little warmth from their host. Their surface temperatures are probably only a few tens of Kelvin. Their skies are dark, save for the faint sweep of the pulsar's beam as it turns. They are believed to have formed from the debris of the supernova that created the pulsar, gathering out of dust and gas in the years after the explosion. These 3 worlds are old. They have been turning quietly around their dead star for about 1 billion years. They are not warm, and they are not lit by anything one might call sunlight, but they are real, and they exist, and the catalogue holds them as the first proof that planets can exist around the strangest of stellar remnants. The names are short and unromantic. PSR-B 1257 plus 12, B. PSR-B 1257 plus 12, C. PSR-B 1257 plus 12, D. Their masses are about 1/40, a few Earth masses. They sit at the cold edge of the catalogue, turning slowly in the light of a clock made of bone. And beyond the named cold record holders, the catalogue hints at many more cold planets we have not yet seen clearly. Most planets in microlensing surveys are cold by design. The method picks up planets on wide orbits, far from the warm parts of their systems. The cold population of the galaxy is probably much larger than the warm one. The warm planets are simply the easiest to find. The galaxy holds vastly more frozen worlds than warm ones, and most of them will never be named. Density is one of the most physically meaningful records the catalogue holds, because density tells you what a planet is actually made of. A rock is denser than ice. Iron is denser than rock. Heavy elements pack more mass into each cubic inch than light ones. When astronomers measure the radius of a planet from its transit and the mass of a planet from its gravitational pull, dividing the two gives them the planet's density. And density tells them softly, indirectly, whether the world is rocky, icy, gassy, or something else. The densest known exoplanet, by the cleanest measurement, is K-38b. Its density is approximately 17 grams per cubic centimeter. To put that in everyday terms, lead has a density of about 11 grams per cubic centimeter. Uranium, the densest naturally abundant element on Earth, has a density of about 19 grams per cubic centimeter. K-38b sits between them, denser than lead, approaching the density of uranium. It is denser than osmium, the densest element you can hold in your hand. Every cubic foot of that planet, if you could lift one out, would weigh more than a small block of stone. The planet has a mass of about 12 Earth masses and a radius of about 1.5 Earth radii, small for its mass, dense for its size. The leading explanation is that the planet is unusually iron-rich, possibly the exposed core of a former larger world that lost most of its rocky mantle long ago to a giant impact. A planet that was bigger once and is now just its heart. Just behind K, 2-38b on the density scale, and far more extreme in its own quiet way, is GJ 367b. This is a small world, only about 3/4 the radius of Earth, only about half of Earth's mass. It is one of the smallest planets in the catalogue, and it is also one of the densest, with a mean density of around 8 grams per cubic centimetre. To match that density, models require the planet to be about 90% iron by mass. It is essentially an iron core, wearing a thin layer of rock. The same kind of physics that gives Earth its small iron heart has, on GJ 367b, eaten almost the entire planet. Its year lasts only 7 hours and 40 minutes. Its day side is hot enough to keep the surface partially molten. It is tidally locked. It sits in the catalogue under a few quiet labels: Submercury, Ultra-Stripped Planet, Iron World. Take any of them softly. A world that is mostly its own core, turning in the light of its sun. At the other end of the density scale, where the catalogue gets gentler, sit the so-called super puff planets, or cotton candy planets. These are worlds whose density is lower than that of cork, lower in some cases than the density of styrofoam. Lower than water they would, if you could find an ocean wide enough and deep enough, float on it. The clearest examples are the 3 planets orbiting the young sun-like star, Kepler, 5.1 Kepler, 5.1b, C, and D. All 3 have radii roughly comparable to Saturn's, but their masses are only a few times Earth's. Their densities are below 1/10 of a gram per cubic centimetre, about 1/10 the density of water. A different early discovery, WASP 17b, has the same kind of property. It is nearly twice the radius of Jupiter, but only about half its mass, with a density of about 0.06 of a gram per cubic centimetre. These are not solid planets. They are vast, bloated atmospheres, held loosely together by gentle gravity, with no clear surface anywhere. They are mostly hydrogen and helium, puffed outward by the heat of their parent stars and the youth of their systems. The puffy planets are a quiet puzzle the catalogue has not fully solved. They exist, but they should be rare. The kind of inflated atmosphere they hold is expected to leak away into space over hundreds of millions of years. Most of the known examples are very young. The systems are only tens of millions of years old. The current best explanation is that they are essentially transient. Planets caught at a moment of their lives when stellar irradiation has puffed up their atmospheres, but the atmospheres have not yet had time to evaporate. Given another billion years, the puffy planets we see today may shrink down into ordinary Neptune-sized or smaller worlds. But for now, in this small slice of cosmic time, they exist. The catalogue holds them softly, worlds the size of giants, light enough to float. The contrast across the density records is the catalogue's whole story in miniature. The same physical laws, gravity gathering material, heat pushing it outward, time slowly settling the balance, produce both a world of compressed iron and a world the consistency of fog. Nothing in the rules forbids either. The dials simply sit at different settings. Both worlds are real. Both worlds turn in the dark right now. The wider catalogue of density measurements has begun to fill in the territory between these extremes. Most rocky exoplanets cluster around densities of 5 or 6 grams per cubic centimeter, roughly Earth-like, with iron cores and silicate mantles. Most large gas giants sit between 0.5 gram and 2 grams per cubic centimeter, depending on their internal heat and structure. The records at the edges are rare. The body of the catalogue is gentler and more uniform. What density tells us, more than anything else, is composition. A world denser than iron is mostly iron. A world less dense than water is mostly gas. The records of density are, in a soft sense, records of what nature has done with the same handful of basic elements when assembled under different gravitational and thermal conditions. The same hydrogen and helium and silicate and iron starting material, sorted and condensed in different ways, produces both K2-38b and Kepler 51c. Nothing exotic. Just the dials turned to opposite settings. Among the records of size, the planet that holds the radius crown is HAT P67b. It is a slightly inflated hot Jupiter with a radius of about 2 Jupiter radii, physically larger than even the densest brown dwarfs, which sit just above the planet star boundary. What makes HAT P67b unusual is not its mass. Its mass is only about 1/3 of Jupiter's, comparable to Saturn's. Its size comes almost entirely from inflation. The upper layers of its atmosphere have been heated and puffed outward by the unrelenting radiation of its host star until the planet is, by volume, larger than any other planet in the confirmed catalogue. Below the surface, where a less irradiated giant would have settled, the heat keeps the atmosphere distended by tens of thousands of miles. Several other planets sit close behind it, in the same enormously bloated class. TRES, 4b, WASP, 79b, WASP, 1-2b, and a handful of newer detections. Most of them have one thing in common. They are very young and very close to very hot stars. Their inflation is not a permanent feature. As their host stars age, and as the planets themselves lose mass slowly to space, they will shrink, deflate, and eventually look quite different from what we see today. The records of size in the catalogue are temporary records. The smallest planets shrink less, the largest planets shrink most. The catalogue's largest worlds today are not the largest worlds of the deep future. At the other end of the size scale, the record holders are more humble. The smallest confirmed exoplanet is Kepler 37b, a world only about 1/3 the size of Earth, slightly smaller than the planet Mercury. It is even smaller than our Moon. It orbits a quiet, sun-like star in a 13-day orbit. Because the planet is so small, the dimming it produces when it crosses in front of its star is extremely faint. Astronomers had to look very carefully to find it. Its host star is bright enough that long, patient observation made the detection possible. For smaller stars, a planet this size would simply have been invisible. The catalogue almost certainly contains many smaller worlds we have not yet seen. The transit method works best on planets that are large compared to their host stars. Around small red dwarfs, smaller planets are detectable. Around larger stars, the detection floor rises. The smallest planet around any star in the catalogue is Kepler 37b. The smallest planets around all stars together are probably much smaller, hovering at the limits of what current instruments can detect, slowly being filled in as observations accumulate. On the question of the most massive planet, the largest in kilograms, not in radius, the catalogue runs into a different problem. there is a boundary, near 13 Jupiter masses, where the definition of a planet starts to blur. Above about 13 Jupiter masses, an object can briefly fuse deuterium in its core. Deuterium is a heavy form of hydrogen that fuses at a lower temperature than ordinary hydrogen. Objects that fuse deuterium are usually called brown dwarfs, failed stars. Below about 13 Jupiter masses, no fusion ever begins. The line is soft. Some astronomers use it to define a planet. Others prefer to define a planet by formation history, regardless of mass. The most massive object, commonly called a planet, near this boundary is something like HD 39091c, about 10 Jupiter masses. A few directly imaged objects sit higher, HR 2562b, at about 30 Jupiter masses, is sometimes called a planet and sometimes called a brown dwarf, depending on the classification used. There are objects more massive still, but at that point the catalogue is not really cataloguing planets anymore. The records of mass do not have a clean ceiling, because the universe does not make a clean break between the largest planets and the smallest stars. The catalogue simply fades upward into the brown dwarfs, and the brown dwarfs fade upward into the smallest stars. You can hold that softly. Somewhere in the catalogue, there are objects that almost lit themselves and didn't. Objects that briefly glowed with deuterium fusion and then went quiet. Objects that sit on the border between worlds and suns and refuse to be cleanly named one or the other. This is a gentler truth than it might at first seem. The boundary between planets and stars is not a wall. It is a gradient. On one end, there are objects so small they can barely hold a thin atmosphere of hydrogen Mercury-like rocky worlds that are essentially exposed cores. On the other end, there are objects so massive their cores are hot enough to fuse hydrogen continuously, lighting the surrounding system with steady warmth. In between, there is a long, quiet spectrum. Super-Earths, mini-Neptunes, Neptunes, Saturns, Jupiters, super-Jupiters, brown dwarfs, the smallest red dwarf stars. The catalogue samples every part of that spectrum. The records are simply the edges of the part where we draw the line and say, this is a planet. The smallest known stars and the largest known planets blur together in mass. Some of the smallest M dwarfs have masses only about 80 Jupiter masses, just above the hydrogen-burning limit. Some of the largest known free-floating planets have masses approaching 30 Jupiter masses, just below where deuterium fusion might briefly happen. The gap between these, the brown dwarf range, has its own population of objects that fuse deuterium for a while, then stop, then cool slowly for the rest of their lives. They are not planets and not stars, and the catalogue of them is its own subject. But the records of mass in the planet catalogue approach that gap softly, and the gap itself is one of the catalogue's quietly fuzzy edges. The shortest year of any confirmed planet in the catalogue belongs to a small, dense, ancient world called PSR J17191438b. It orbits a pulsar at a distance of only about 600,000 kilometers, less than twice the distance from the Earth to the Moon, and its year lasts approximately 2 hours and 10 minutes. 2 hours and 10 minutes is the time it takes for the planet to complete one full orbit around its sun. In the time it takes you to fall asleep tonight, this planet will complete a year, and then another, and then most of another. It is a planet that turns around its sun more than 10 times in a single Earth day. The story of this world is, in its quiet way, one of the strangest in the catalogue. It is believed to be the stripped core of a former white dwarf, a small dead star that was once the companion of the pulsar. Over billions of years, the the pulsar drew most of its companion's mass away into a thin accretion stream, slowly eating it. What was left behind was a compact remnant, about Jupiter in mass but much smaller in size, only Saturn in radius. Its density is enormous. Its composition is mostly carbon and oxygen, the kind of carbon-oxygen mix that makes up the interior of any small white dwarf. Compressed by gravity over billions of years, the carbon may have crystallized. Some descriptions of this planet, in the language of astronomy, call it a diamond planet. The name is more poetic than rigorous. Whether or not its interior actually forms a single crystal, the planet is real, and it is dense, and it turns around its dead star twice every Earth hour, every Earth night, every Earth year, for as long as the catalogue will keep track of it. At the other end of the orbital scale, the longest known years belong to directly imaged planets on very wide orbits. The clearest record holder is a young world called Coconuts, 2b. It orbits its host star at a distance of about 6,471 astronomical units. An astronomical unit is the distance from the Earth to the Sunday. The planet sits roughly 6,000 times that distance from its Sun. For comparison, the Sun's nearest stable gravitational holding is the Oort cloud, which extends to perhaps 1 or 2 light-years, about 100,000 astronomical units. Coconuts, 2b, is not quite at the edge of its system, but it is well past anything that exists in the solar system's planetary region. Its orbital period, its year, lasts more than 1 million Earth years. Imagine that very softly. On Coconuts, 2b, one single year is longer than the entire history of human civilization. Longer than the time since modern humans first painted on cave walls. Longer than the entire span of any cultural memory we possess. The planet has been in its current orbit for tens or hundreds of orbits since it formed. Each orbit is a long, slow turn through the cold outer regions of its system, with its host star, a faint red dwarf, appearing as a slightly brighter star among many. The planet's mass is about 6 Jupiter masses. It is young, only a few 100 million years old, and still warm with the heat of its own formation, warm enough that its infrared glow outshines what little light it receives from its sun. From the planet's surface, the host star would be visible only as a small bright point, not bright enough to count as daytime. The world is its own warmth. Other planets sit on similarly long orbits. HD 106906 B orbits its host stars at a distance of about 738 astronomical units, with an orbital period of more than 15,000 years. Its hosts are a binary pair. From the planet's sky, the 2 suns appear as 2 bright stars in an otherwise dark sky. The planet is believed to have been gravitationally scattered into its current orbit by an encounter with another body in the system long ago. The orbit you see today is the long-faded memory of an old encounter. You can imagine these planets softly worlds, whose years are longer than human history, turning patiently around their faint, distant suns, no nearer to them than the outer edge of our own solar system. The most stretched orbit in the entire catalogue, the most eccentric, belongs to HD 20782b. Most exoplanet orbits are roughly circular, modest eccentricities, gentle ovals. A few are outliers. HD 20782b has an eccentricity of approximately 0.97. To picture what that means, you can compare. Earth's eccentricity is 0.017, a nearly perfect circle. Halley's Comet has an eccentricity of about 0.97. HD 20782b orbits its star on a path that looks much more like the path of a comet than like the path of a world. Its distance from its Sun varies between about a 16th of an astronomical unit at periastron, the closest approach, and about 2.5 astronomical units at apastron, the farthest point. Inside a single year, the planet sweeps past its Sun, closer than Mercury sweeps past ours, then drifts outward, past where Mars would be, then turns around and comes back. The temperature on the planet varies wildly with its orbit. At the close pass, models suggest the upper atmosphere can reach temperatures of 1500 Kelvin, hot enough to glow softly. At the far end, the planet may cool back down to a few hundred Kelvin, dim and patient, waiting for the next slow inward sweep. The planet is heated, then cools, then heated again, every year, forever. A few thousand years from now, 1,000 of those cycles will have passed. A few million years from now, 1,000,000 of them. Most planets do not orbit this way. The few that do are believed to have been scattered into their stretched orbits by close encounters with other planets early in their system's histories. Encounters that ejected some siblings into interstellar space and threw others into long looping orbits. The orbits you see today carry the memory of those old encounters, hundreds of millions or billions of years after the encounters themselves. The catalogue holds those orbits softly. Planets whose paths around their suns are not the gentle rounds of stable worlds, but the long, stretched loops of survivors. And finally, among the orbital oddities, there is the small group of planets that orbit their stars backward, or sideways, or upside down. Most planets orbit in the same direction. Their host stars rotate, a natural consequence of the way both formed from the same swirling disk of gas and dust. A few do not. HAT, P, 7b, WASP, 17b, and WASP, 33b, all orbit in retrograde against the spin of their suns. HATP, 7b in particular, is tilted at nearly 180 degrees relative to its star's equator. The clearest extreme case of a polar orbit is WASP, 79b, whose path takes it over the star's poles instead of across its equator. These tilts and reversals tell a soft story of violent youth. Each planet was almost certainly knocked into its current orbit by a gravitational encounter with another world during the system's formation. The current quiet path was not the original one. The orbit remembers an old encounter the rest of the system has long forgotten. The mechanism most commonly proposed for these tilted orbits is called Kozai-Lidov oscillation. It is a soft, slow gravitational dance. When a planet has a distant companion, another planet, or a binary star, or even a passing object, the gravitational pull of the companion can, over millions of years, gradually trade off between the planet's orbital eccentricity and its orbital inclination. The orbit slowly stretches, the inclination slowly tilts. The exchange is reversible, and the orbit can swing back. But if at any point during the swing the planet comes close enough to its star that tidal forces become significant, the orbit can be partially locked in the eccentricity, damped down by tidal dissipation, the inclination frozen at whatever angle it had when the lock happened. The end result is a planet on a tilted or retrograde orbit, with no obvious reason for it to be tilted today, with the responsible companion possibly long gone. This means that retrograde and polar orbits in the catalogue are, in a soft sense, fossils. They are records of long-vanished gravitational neighbors. The planet you see today, on its strange tilted orbit, was once part of a richer system that has since been simplified. Some of the original siblings may have been ejected entirely, becoming rogue planets. Others may still be there, hidden, too small or too far out to have been detected yet. The orbit is the only memory left, and eccentric orbits, like HD 20782b's, tell a related but slightly different story. The eccentricity of nearly a comet is not a stable configuration unless the planet either had a violent encounter recently or is being continuously perturbed by a hidden companion. Most analyses prefer the past encounter explanation. An old gravitational scattering, billions of years ago, left the planet on its current stretched path, and the path has been preserved since because nothing has happened to round it out. The planet is, in this sense, also a fossil of an older system. The catalogue holds fossils softly, all along its more extreme orbital records. The catalogue of exoplanets is mostly local. Most of the worlds we know about sit within a few hundred to a few thousand light-years of the Sunday. The methods we use, small dips in starlight, small wobbles in stellar motion, work best when the host stars are bright enough to study in detail. Beyond a few thousand light-years, the signal fades, and only the most dramatic detections survive the dimness. The farthest confirmed exoplanet in the standard catalogue is Sweeps 1-1, sometimes joined by Sweeps 0-4, a pair of hot Jupiters discovered in the galactic bulge during a deep transit survey toward the center of the Milky Way. They sit at a distance of approximately 27,000 light-years. That distance is almost as far as the distance from the Sun to the center of the galaxy. The planets were detected because the survey was looking at an enormous number of stars, at once millions of them, and the few transits among those millions stood out against the background. Sweeps 1-1 has a year of about a day and a half. Its star is too faint and too distant for follow-up observation to characterize it further. The planet exists in the catalogue as a small named fact, far away in the bulge. Beyond that, the catalogue reaches further still, but only through indirect means. The most distant candidate exoplanet ever proposed is a small possible planet detected through the dimming of an X-ray binary in the Whirlpool galaxy Messier 51, at a distance of about 23 million light-years. The candidate is informally called M51UL S1b. If it is real, it would be the first planet ever detected in another galaxy. The detection is a single event, one dimming of the X-ray source, and the candidate cannot be reobserved anytime soon. The planet, if it exists, will not transit the same source again for decades. We have, possibly, seen one world in another galaxy exactly once. Whether or not it ever was a planet, the act of looking was itself extraordinary. The catalogue reaching, just briefly, beyond the Milky Way. You can hold that softly. A world so far away that its starlight is older than the human species. A small, dim signal carried through 23 million light-years of intergalactic medium, arriving at Earth as a single faint dip in an X-ray source's brightness, and then ending. Whatever it was, it is still there, doing what it does, unaware that we ever saw it. At the other end of the distance scale, the records are much closer. The nearest known exoplanet to Earth is Proxima Centauri b, orbiting the small red dwarf Proxima Centauri at a distance of 4¼ light-years. Proxima is the closest known star to the Sunday. The planet sits in its star's habitable zone, the narrow band of distances at which liquid water could, in principle, exist on a surface. Its mass is about 1/700th times the mass of Earth. Its year lasts only 11 days. Its sun is much smaller and cooler than ours, so the habitable zone sits much closer in. Whether Proxima Centauri b is actually habitable is an open question. The planet is almost certainly tidally locked, one side facing its sun forever, the other facing forever into the dark. Its star is also a flaring star. Red dwarfs emit frequent strong flares, especially when they are young, and these flares can strip thin atmospheres from nearby planets. Whether Proxima Centauri b has any atmosphere left, and what kind, is something we will probably learn over the coming decades. 2 more planets sit in the same Proxima system. Proxima c orbits further out, in a colder orbit, with a year of about 5 Earth years. Proxima d sits even closer in than Proxima b, on a 5-day orbit, smaller and warmer than its siblings. Our nearest stellar neighbor is, it turns out, a system of multiple worlds. 3 planets, 1 small red star, 4¼ light-years away. The closeness is not abstract. If you were able to send a signal, a single radio pulse toward Proxima now, the pulse would arrive there in just over 4 years. If something were to respond instantly, the response would reach us a little over 4 years after that. From a galactic perspective, that is essentially next door. Among stars more similar to the Sun yellow dwarfs of spectral type F, G, or early K, the closest known exoplanet is Alpha Centauri bb, orbiting one of the 2 Sun-like stars in the triple Alpha Centauri system. It is a small, hot world on a 3-day orbit. Its existence has been debated for years. Some analyses have argued that the small radial velocity signal that suggested the planet was actually a stellar artifact, and other analyses have argued it is real. More recently, a direct imaging campaign with the largest space telescope ever built has produced a stronger candidate, a possible planet imaged directly near Alpha Centauri A, the slightly larger of the 2 Sun-like stars in the system. If confirmed, that planet would become the closest known exoplanet around a Sun-like star, and it would sit within or near the habitable zone of that star. It would be, almost certainly, the best candidate for a future interstellar mission anyone has ever found. The system itself is one of the more interesting in the neighborhood. Alpha Centauri A and B are a tight binary, orbiting each other in about 80 years. Proxima Centauri orbits them both at a much wider distance, far enough out that its connection to the inner pair was only confirmed relatively recently. From a planet near Alpha Centauri A, the sky would hold 2 bright suns, one of them yellow and sun-like, the other slightly orange, and somewhere among the night stars, the faint red point of Proxima, the most distant member of the system, more like a far companion than a 3rd sun. The catalogue holds this possible 2nd Sun and Earth softly, with confirmation pending. We are not certain it is there. If it is there, it is closer than anything else of its kind we know. A few other nearby planetary systems deserve a soft mention here, because the distance records are not only about the absolute closest, but also about the structure of the local neighborhood. Barnard's star, the 2nd closest stellar neighbor to the Sun, at about 6 light-years, was long thought to host a planet on a few 100-day orbit, and recent analyses have revived the case for a small planet there. TRAPPIST-1, with its 7 worlds and resonance chain, sits about 40 light-years away, close enough that several of its planets are real targets for detailed atmospheric study. The Wolf 1061 system, at about 14 light-years, holds 3 confirmed planets, one of them in the conservative habitable zone. The local stellar neighborhood, when mapped by planets rather than by stars, is dense with possibilities. What this means, very softly, is that the catalogue of the nearest exoplanets is filling in. A decade ago, the closest known confirmed exoplanet was many tens of light-years away. Today it is 4¼ The trend is unlikely to change directions. As techniques improve and as observations accumulate, the number of confirmed planets within 10 or 20 light-years of the Sun will continue to grow. Each new addition becomes a candidate for future direct study, the kind of observation where a telescope might one day separate the light of the planet from the light of its star, and read its atmosphere directly. Most of those candidates have not been found yet. The closest one might already exist in the catalogue. The closest one of a few decades from now is probably orbiting a star we have already named, in a system we have already looked at, on an orbit we have not yet measured precisely enough to call confirmed. And from a great distance, say, from a planet around a star in the galactic bulge, looking outward toward the disk, the Sun itself would appear as one small, unremarkable point among hundreds of millions of others. Its planets would be invisible without very careful effort. Were astronomers on a planet in the bulge to compile their own catalogue of nearby exoplanets, the Sun's family of 8 worlds would not be on it. The Sun would be too dim, too far away, too uninteresting against the bright crowd. Distance, in the exoplanet catalogue, cuts both ways. The reason the catalogue has the distance distribution it has is the reason any catalogue of stars has its own distance distribution. Light fades with distance, and at some point the light drops below the limits of any instrument. For an exoplanet, the relevant signal is even fainter than the starlight, a small dip during a transit, a small wobble in radial velocity, a small reflected glow during a phase curve, a small lensing ripple during a brief alignment. Each method has its own distance limit. Transit photometry works best within a few thousand light years. Radial velocity, with the current generation of spectrographs, works out to similar distances for bright enough stars. Direct imaging works for nearby young systems with planets on wide orbits. Microlensing reaches the deepest into the galactic bulge, but produces single-event detections that cannot easily be reobserved. This means the geography of the catalogue is not the geography of the galaxy. The catalogue is densest, where the methods work best in a roughly spherical region around the Sun, with a long, thin extension toward the galactic center along the microlensing surveys. Most of the Milky Way remains, for exoplanet purposes, dark. There are stars by the hundreds of billions in the parts of the galaxy we cannot probe yet. Each of those stars almost certainly has at least one planet on average. The galaxy is much fuller of worlds than the catalogue can yet show. There are planets that drink almost all the light their suns send to them, and there are planets that throw most of that light back. The catalogue includes the most extreme example of each. The darkest known exoplanet is TRES, 2b, a hot Jupiter whose geometric albedo, the fraction of incident starlight it reflects, is approximately 1%. Coal has an albedo of about 5%. Fresh asphalt has an albedo of about 10. Earth, on average, reflects about 37% of the light that reaches it. Venus reflects about 70. TRES, 2b returns only about 1%. It is darker than coal, darker than the blackest paint humans have ever produced. The light that reaches the planet's atmosphere is absorbed almost entirely, swallowed into the gas. The planet does not shine. It glows only faintly in the long wavelength dim red afterheat of the radiation it has absorbed. The atmosphere of TRES, 2b, is thought to contain heavy chemical absorbers, sodium, potassium, and titanium oxide molecules that swallow nearly every photon of visible light. The planet is hot, equilibrium temperature, around 1500 Kelvin, but the heat does not make it shine in the way the night side of a normal hot Jupiter does. Instead, the heat radiates outward in deep red and infrared wavelengths, while the visible light spectrum stays nearly black. From a great distance, against the bright disk of its parent star, the planet would appear as a small absorbing spot, a deeper darkness against the star's light, rather than a reflected glow. At the other extreme of the same scale sits LTT 9779b, an ultra-hot Neptune whose geometric albedo is about 80%. The planet returns 4/5 of the light its sun sends to it. The day side acts almost like a mirror in space. The cause is believed to be a thin, high-altitude layer of silicate or metal clouds, possibly tiny droplets of titanium or silicon, frozen into reflective haze by the strong winds that move heat from the day side to the night side. The planet is roughly 4.5 Earth radii across, with a mass of about 29 Earth masses on a 19-hour orbit. Its host star is bright enough that the reflected light from the planet is detectable in careful observations. The planet also sits inside what astronomers call the hot Neptune desert, a region of orbit-sized space where Neptune-sized worlds are conspicuously rare. Most Neptune-sized planets, when placed on tight orbits, are expected to lose their atmospheres quickly to stellar irradiation and shrink down into smaller rocky worlds. The desert is the visible signature of that loss, an area of the catalogue with very few inhabitants. LTT 9779b is one of those few. Why it has survived where so many others have not is one of the catalogue's open puzzles. The leading guess is that the highly reflective cloud layer is keeping the planet's upper atmosphere cool enough to slow the rate of escape, but the case is not closed. The planet sits there softly, bright in the sky, a small mirror among the wider catalogue. Between these two extremes, the darkest and the brightest, sit a small number of planets where the atmosphere has produced strange and specific weather. HD 189733b is a deep cobalt blue Jupiter, 64 light-years away. Its color was the first ever measured for a planet beyond the solar system, detected through the change in starlight as the planet passed in front of and behind its host. The blue is not a reflection of an ocean. The planet has no ocean. The blue comes from silicate clouds, tiny droplets of glass at high altitudes that scatter the blue light of the star, while heavier wavelengths are absorbed by the gas below. The same silicate droplets on the cooler night side condense into actual molten glass rain. The terminator between dayside and nightside is whipped by tidal locked winds at speeds of more than 4,000 miles per hour. The glass droplets fall horizontally, blown sideways across the entire planet by the relentless wind, a close cousin of HD 189733. B is WASP 76b, where the chemistry is different and the weather is even stranger. WASP 76b is hot enough on its dayside that iron itself vaporizes into the atmosphere. The dayside to nightside winds carry the iron vapor toward the cooler nightside, where it condenses. On the nightside, iron rain falls. Liquid metal droplets blown sideways by supersonic winds. The dayside glows hot with the emission of sodium and other metal vapors. The terminator is the strangest weather front in the catalogue. On one side, glowing hot metal vapor. On the other, slow metallic rain. These two worlds, one with glass weather, the other with iron weather, are not the only ones of their kind. Several other hot Jupiters are believed to share similar atmospheric circulation patterns. Some catalogues of hot Jupiter weather include the speculative possibility that other ultra-hot Jupiters may also rain materials we would not normally think of as rain corundum, the mineral that makes rubies and sapphires, on Hat P7b, quartz, and silica, on a small handful of others. The catalogue of weathers in the catalogue of planets is large enough to be its own document. The records of light are simply the visible faces of those weathers. Among the smaller members of the same atmospheric family, GJ 1214, BA sub Neptune, about 48 light-years away, has a thick, hazy atmosphere of heavy molecules that scatters incoming light so thoroughly that astronomers had to look across many wavelengths to detect anything specific in its composition. The planet has been called a water world wrapped in steam because its atmosphere may contain a large fraction of water vapor at high pressure. The haze is interpreted as a layer of small particles, perhaps salt grains, perhaps photochemical organic molecules, perhaps something else that absorbs and scatters light fairly uniformly. The world is colored less brightly than a Jupiter and less darkly than Tres, 2b somewhere in between, with its surface temperature around 280 Kelvin under the haze, possibly with liquid water somewhere in its layered envelope. A still different kind of atmospheric record belongs to the planets that are slowly evaporating, like Osiris, HD 209458b, discussed at length in the records of atmosphere, but also like HATP 32b, Kelt 9b, and a small set of others. The atmospheric loss leaves a thin tail of escaping gas behind the planet. Over time, that tail spreads out and disperses, leaving no permanent trace. The planet keeps moving. The next time around, a new tail forms. The cycle is slow and steady, and the visible weather it produces is the steady streaming of gas behind the planet as it orbits. You can let these images sit gently. Glass rain on one world, iron rain on another, heavy haze covering a third, slow gas streaming behind a fourth, all of it real weather, all of it real chemistry, all of it happening right now, somewhere out there in the dark, on worlds nobody has visited. Some planets in the catalogue are very, very old. Older than the Milky Way's disk in some cases. Older than nearly every star you can see at night. The oldest known exoplanet is the world informally called Methuselah, formally catalogued as PSRB 162026b. It orbits a binary system of a pulsar and a white dwarf inside the ancient globular cluster, Messier 4, at a distance of about 12,400 light-years. Its age is estimated at approximately 12.5 billion years. That is only a billion years younger than the universe itself. Methuselah formed when the universe was less than a tenth of its current age. The chemistry of its environment then was nothing like the chemistry of the solar system today. The first generations of stars had not yet enriched the galaxy with most of the heavy elements that planets are made of. Iron, magnesium, silicon, oxygen, all the building blocks of rocky planets were rare. Most planet formation models predicted that worlds simply could not form in such metal-poor environments. Methuselah's existence quietly disproved that. The planet is real. It is a Jupiter-mass world in a wide, stable orbit around its binary host, inside a globular cluster of ancient stars, all about the same age. It has been turning quietly through the cluster for almost the entire history of the universe. The sky above Methuselah is full of close stars. Globular clusters are dense, but the planet itself is patient, ancient, doing what planets do. The youngest known planets are at the opposite end of cosmic time. The clearest examples are the planets in the PDS-70 system, where two confirmed worlds, PDS-70b and PDS-70c, are currently in the process of forming. The system is only about 5 million years old. The planets are still embedded in their parent star's protoplanetary disk, the swirling cloud of dust and gas left over from the star's birth. They are still gathering material from that cloud. They are still growing. Direct imaging of the PDS-70 system has caught the planets in unusual detail. Each one is surrounded by its own small disk, a circumplanetary disk, a smaller cloud of dust and gas that orbits the planet itself and feeds it. These are the only known exoplanets with directly observed circumplanetary disks. They give us, softly, a window into how planets are made, the slow process of accumulation, the infalling material, the warming of the new world as gravity packs more matter into it. They are not finished. They will continue to grow for tens of millions of years. The final masses they will reach are not yet known. In our timescale, they are infants. In their own timescale, they are caught at the moment of their formation, doing what every planet in the older catalogue has long since stopped doing. Between the very old and the very young, there are systems that fall somewhere in the middle but are remarkable for what they reveal. Kepler 444 is a 5-planet system around a sun-like star that is about 11.25 billion years old. The system is more than twice as old as the Sunday. All 5 planets are small, all rocky, all on tight inner orbits. The configuration is a compact, mature, calmly turning planetary system from a time long before the Earth existed. If life requires worlds with a few billion years of stable history, the planets of Kepler 444 or their long-vanished cousins around long-vanished stars have had more time to host life than the Earth has. Whether any of them did is an entirely separate question we cannot yet answer. The wider catalogue of ancient planets is small but growing. A few other known exoplanet systems sit at ages of 9 or 10 billion years, comfortably older than the Sun, comfortably younger than Methuselah. Among the named systems, Kepler 444 is the clearest example, but other Sun-like star systems with confirmed planets in this age range include Kepler 10 and several stars in the so-called thick disk of the Milky Way, the older population that orbits at slight tilts to the main disk. Most ancient planets are found around metal-poor stars because metal-rich stars only became common in the galaxy more recently. The old population is a window into how the galaxy made worlds when the chemistry was simpler. At the young end of the catalogue, PDS 70 is not the only system caught mid-formation. A handful of other very young systems, HD 100546, MWC 758, HL Tau, AB Aurigae, show signatures consistent with planets currently forming in their disks. These detections are usually less definitive than PDS 70s because the disks themselves complicate the observations. But the catalogue grows slowly here too. Over the next decade, more young systems will be characterized in finer detail, and a clearer picture of planet formation in real time will emerge. The youngest planets you can see right now might be the older planets of a few decades from now, gradually clearing their disks and settling into stable orbits. The picture across the age records is gentle. The galaxy has been making planets nearly the whole time it has existed. The oldest stars made the oldest planets. The youngest stars are making them right now. Somewhere on a slow line between the two, the Sun and Earth fit comfortably, neither pioneers nor latecomers, just one ordinary system among many. A soft thought to hold on the age records is that the universe is, in cosmic terms, still young. The current age of the universe is about 13.8 billion years. The oldest planets are about 12.5 billion years old, the youngest about 5 million. Compared to the long, deep future timescales over which the universe will continue to make stars and planets possibly trillions of years, if the smallest red dwarfs keep burning their fuel slowly enough, the entire current population of exoplanets in the catalogue represents an early sliver of cosmic history. Most planets that will ever exist have not yet been made. The catalogue of the future will be much larger than the catalogue of today, and most of its planets will form long after the Sun and Earth are gone. The records you have heard tonight are records of an early chapter in a very long book. There are planets in the catalogue whose atmospheres we know almost nothing about, and there are planets whose atmospheres we have studied for decades. The most thoroughly mapped atmosphere of any exoplanet belongs to HD 1-89733b, the silicate glass rain world, from the Records of Light section. Because the planet is relatively close, only about 64 light-years away, and because it is large and bright and well placed for repeat observation, astronomers have measured its color, its atmospheric scattering profile, its sodium and potassium and water vapor absorption lines, its thermal day-night contrast, and the wind speeds at its terminator. It is the closest thing astronomers have to a reference planet beyond the solar system. Most of what we know about how hot Jupiter's work we have learned by patiently watching HD 1-89733b across decades. The first exoplanet around which water vapor was unambiguously detected was HD 209458b, sometimes called Osiris. The discovery was made through transit spectroscopy. As the planet passed in front of its star, a small fraction of the star's light filtered through the planet's upper atmosphere on its way to Earth. The starlight carried, in its precise wavelengths, the absorption fingerprints of every molecule it had passed through. Among those fingerprints, the unambiguous signature of water vapor. It was the first time anyone had measured what an alien atmosphere was made of. The technique has since been used on dozens of planets, including most of the records in this catalogue. The first time it worked on Osiris. Osiris also became the first exoplanet observed losing its atmosphere. The planet sits close to its host star, and the upper layers of its hydrogen-rich atmosphere are heated to thousands of degrees, hot enough to escape the planet's gravity entirely. A thin, trailing stream of hot hydrogen extends behind the planet as it orbits. The mass loss rate is enormous, in absolute terms thousands of tons of hydrogen per second, but small compared to the planet's total mass. Osiris will lose only a small fraction of its bulk over the lifetime of its star. But the loss is real, and it has been measured, and the technique of measuring it has since been applied to many other planets. Among the smaller worlds in the catalogue, the most discussed atmosphere in recent years is K2-18b. K2-18b is a small, temperate sub-Neptune, a world about 2.5 times the radius of Earth and about 8.5 times its mass, on a 33-day orbit around a small red dwarf in the habitable zone of its host star. The planet has been catalogued as a leading candidate for a class of worlds called Haitian planets, planets with thick hydrogen atmospheres above global liquid water oceans. If Haitian worlds exist, K2-18b is the strongest candidate so far. The detection of water vapor in its atmosphere came first, then methane, then carbon dioxide. The molecules are consistent with the Haitian interpretation, though they do not prove it on their own. The more recent and more debated detection in K2-18b's atmosphere is the tentative signature of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine microbial life phytoplankton in the oceans. If the signature in K2-18b's atmosphere is real, the molecule has either been produced by biology or by some chemical process we have not yet identified on a planet of its kind. The interpretation is contested. Some analyses do not see the signature at all. Others see it weakly. None of the current observations is decisive. The catalogue holds K2-18b softly. A world that may be an ocean planet. A world that may be the first to give us a biological hint. A world that is, at minimum, the most interesting small temperate planet we have ever found. You can let this sit gently. Whatever the answer turns out to be for K2-18b, the patient, slow process of studying it is what matters. Each observation adds a little more. Each year, the picture sharpens slightly. The catalogue does not produce sudden answers. It produces accumulating evidence, slowly, over many years. The world is real, far away, doing what it does. We are simply learning to see it more clearly. A different kind of atmospheric record belongs to WASP 39b, a Saturn mass hot world whose atmosphere was one of the first to be studied in fine spectroscopic detail by the most recent generation of space telescopes. WASP 39b's atmosphere contains the unambiguous signatures of carbon dioxide, sulfur dioxide, water vapor, sodium, potassium, and several other common molecules, a complete atmospheric chemistry mapped softly through transit spectroscopy. Each absorption line is a small fingerprint, and the planet has, over the past few years, become one of the most chemically detailed exoplanetary atmospheres in the catalogue. The atmospheric techniques have also been used on smaller, more temperate planets. TOI 1452b is a small ocean world candidate about 100 light-years away, on a wider orbit around a small red dwarf, with a density consistent with a global water ocean covering a rocky core. Its atmosphere has not yet been characterized in fine detail, but the planet's bulk properties, its size, mass, and density, make it one of the more promising, small temperate worlds for future study. The catalogue of temperate worlds with known bulk densities is growing slowly, and TOI 1452b sits among them as one of the gentlest entries. Across the wider catalogue, water vapor has now been detected unambiguously in dozens of exoplanetary atmospheres, methane in several, carbon dioxide in many of the more recent observations. The wider chemistry of hot Jupiters and Neptunes is becoming, very gradually, a real chemistry, not just a series of single detections, but a population of measurements across many worlds. The records of atmosphere are softening into a body of knowledge that future videos will be able to revisit. The same technique, transit spectroscopy, is being slowly extended to the smaller and cooler worlds in the catalogue. A few rocky worlds, including some of the TRAPPIST-1 planets, have been observed during transit, and the upper limits on their atmospheres have been measured. The current observations cannot yet rule out thin atmospheres on all of those worlds, but they have begun to put soft constraints on what kinds of atmospheres might be present. Over the next decade or two, the same kind of careful spectroscopic work will be applied to many more small temperate worlds. The records of atmosphere will gradually include more rocky worlds, more habitable zone candidates, more sub-Neptunes with detailed compositions. The catalogue of what is known, in this corner, will softly thicken. The catalogue holds not only individual extreme planets, but also extreme systems. The most populous known planetary system is TRAPPIST-1, a small ultracool dwarf star about 40 light-years away. 7 confirmed planets orbit it, all roughly Earth-sized, all on tightly packed inner orbits. The planets are catalogued as TRAPPIST 1b, c, d, e, f, g, and h. Their orbital periods range from 1.5 days to 19 days. 3 of them, D, E, and F, sit inside the conservative habitable zone of their host star. The most extraordinary feature of TRAPPIST-1 is not just that it has 7 planets, but that the planets are locked in mutual orbital resonance. For every pair of neighboring planets, the orbital periods relate in small whole number ratios. Across all 7 planets, the resonance chain follows the precise pattern: 24 to 15, to 9 to 6, to 4, to 3, to 2. These ratios are among the most precise resonance chains ever observed in any planetary system. The planets keep time with each other, every orbit, every year, for as long as the catalogue has watched them. From the surface of any one TRAPPIST world, the other planets in the system would appear as small disks, roughly the size of the Moon, as seen from Earth, sometimes nearer, sometimes further. On certain days, you would see 2 or 3 of your neighbors at once, lined up in the sky. The host star is small and dim and red, so the sky would not be bright. The planets would loom larger in the sky than the Sun itself. The system is a soft constellation of small worlds, dancing in time around their faint red center, all of them probably tidally locked, each one a small world with its own permanent day and permanent night. A different kind of architectural record belongs to the planets that sit on the tightest possible orbits, worlds so close to their host stars that the planet's surface lies inside the star's corona. Several record holders share this property. The most extreme is Kepler 1520b, a small rocky world whose year lasts only about 16 Earth hours. The planet is actively disintegrating. Its surface is being slowly vaporized by the heat of its sun, and the vapor dust and gas mostly is being blown off into space behind the planet, forming a comet-like tail. Each transit of Kepler 1520b across its host star produces an asymmetric dip in starlight, sharp at the beginning, slow and trailing at the end, because the planet's dust tail extends out behind it. The planet is losing hundreds of millions of tons of mass per second. Its expected remaining lifetime is on the order of 100 million years. It will eventually be vaporized entirely, dissolved into a long, thin trail of dust that will itself disperse into the orbital plane of the system. A small planet softly becoming nothing. Several other planets are caught in similar states. K 22b KOI 2700b and the candidate KIC 12557-548b all show signatures of disintegration in the same way. They are all small rocky worlds on ultra-short period orbits. They are the catalogue's reminder that planets are not permanent. The galaxy makes them, and the galaxy can also slowly take them apart, given enough heat and time. On the other side of the architectural records, some planets orbit not one star, but 2 or 3 or 4. The clearest example of a planet with multiple suns in its sky is HD 188753, Ab, a hot Jupiter in a triple star system about 149 light-years away. The planet orbits one of the stars, and the other 2 stars orbit each other as a tight pair, which in turn orbits the primary at a wider distance. From the planet's sky, 3 suns would appear at different times of day and night, one close and bright, 2 further, but still daylight strong. The night never quite arrives in the way it does in single-star systems. Even more striking is Kepler 64b, often called PH1b, after the citizen scientists who helped find it. The planet orbits 2 stars, a tight binary, locked in a close mutual orbit, and a second pair of distant stars orbits them all. The system has 4 stars in total. The planet is a circumbinary world, meaning it orbits both of the close binary stars at once on a wider orbit than the binary's own. From the planet's surface, the sky would hold 2 close suns rising and setting on slightly offset schedules, plus the second pair as bright stars somewhere in the wider sky. The visible sky has more than one source of daylight. The shadows of standing objects would never quite match up. A simpler kind of circumbinary architecture is held by Kepler 1.6b, the first confirmed circumbinary planet, often described in popular media as a real-world Tatooine. It is a Saturn mass world orbiting a tight pair of small stars on a wide, slow orbit. The two stars rise together, sometimes apart, depending on where in their mutual orbit they happen to be. The shadows on Kepler 1.6b come in pairs, sometimes overlapping into one, sometimes splitting into two. The wider circumbinary catalogue includes Kepler 3.4b, Kepler 3.5b, Kepler 3.8b, Kepler 4.7b and c, a two-planet circumbinary system, Kepler 4.5.3b, and Kepler 1.6.4.7b. Each one is a soft variation on the same theme: planets that have somehow stabilized themselves in a region of orbital space that early models thought should be too turbulent for planets to survive. They do exist. The catalogue has more than a dozen of them. Some of them may be common. The harder-to-detect rocky circumbinaries simply do not show up in the existing surveys yet. The catalogue of two-sun worlds is probably much larger than what we have so far seen. The other architectural records in the catalogue include systems where the planets sit in very specific resonant configurations, besides TRAPPIST-1. The Gliese 876 system has 3 planets in a Laplace resonance, a configuration where 3 orbits are linked in a small whole number ratio, the same kind of resonance found among 3 of Jupiter's Galilean moons. The Kepler 223 system has 4 planets in a 4-body resonance. The Kepler 90 system has 8 planets, briefly tying the solar system for the record of most populous planetary system before TRAPPIST. One reclaimed it with its 7 smaller worlds. The HD 10180 system holds at least 6 confirmed planets, and possibly several more, on a wide range of orbits around a sun-like star. Each of these systems is a small architectural record in its own right, proof that nature can stabilize many planets together, often in carefully timed orbital relationships. Among the systems with 2 stars, the structural variety is also surprising. There are S-type binary systems, where the planet orbits one star of a binary pair with the other star as a distant companion that does not directly affect the planet's orbit. The Alpha Centauri system, if its planets are confirmed, would be an S-type binary configuration, Alpha Centauri A and B, as a tight pair, with the planets orbiting one of them, while Proxima orbits both from a much greater distance. There are P-type binary systems, the circumbinary systems already discussed, where the planet orbits both stars at once on a wider orbit. There are also type binary configurations, where a planet sits in a triangular gravitational equilibrium with 2 stars, though no confirmed type exoplanets have been found. Each architectural record is itself a small case study in what kinds of gravitational geometry can hold worlds stably. The catalogue is, in this sense, also a catalogue of stabilities. The fact that we keep finding more configurations means that more configurations are possible than older models predicted. The galaxy makes its planetary systems with surprising creativity. The stability of circumbinary planets, in particular, was once thought to be far more limited than it has turned out to be. Early dynamical models suggested that the chaotic gravitational fields close to a binary star pair would prevent planets from forming or surviving on close orbits, and so circumbinary planets, if they existed, would be rare and far from their hosts. The catalogue has shown otherwise. The known circumbinary planets are not particularly far from their stars. Many sit just outside the dynamical stability limit, which is itself a smaller distance than was assumed. Nature, in this case, has been more flexible than the early models predicted. The Kepler 4-7 system, with its 2 confirmed circumbinary planets, even includes a planet in the conservative habitable zone of the binary host, a world that could in principle hold liquid water in a sky with 2 suns. Not every planet has a sun. Some planets, many planets, orbit no star at all. They drift through interstellar space, unbound to any system, on slow trajectories that may take them tens of millions of years to cross even the inner edge of any nearby gravitational well. They are called free-floating planets, or rogue planets, or nomad worlds. The first confirmed free-floating planet was PSO J318 5-22, a young Jupiter mass world only about 80 light-years from Earth. It is young, only about 80 million years old, and still warm with the heat of its own formation. It glows faintly in the infrared, with internal temperatures around 1100 Kelvin. Its atmosphere is full of dust clouds and methane absorption features. From the planet's surface, if you could stand on it, the sky would be black. No sun. No bright star nearby. Just the slow drift of the local stellar neighborhood, with the brightest stars appearing as small, bright points among the many distant ones. The planet is its own light source, not bright, but warm. And the only weather is the slow circulation of the dust clouds in its own atmosphere. The wider population of rogue planets is believed to be enormous. Some surveys, based on gravitational microlensing data, have suggested that there are at least as many rogue planets in the Milky Way as there are stars, possibly several times as many. The lower mass limit of what counts as a planet runs into the same boundary issue as the high mass limit. At very small masses, rogue objects shade into the population of brown dwarfs and beyond, into the small body's population that is essentially interstellar dust. But somewhere in the middle, the Jupiter mass and Saturn mass and Earth mass rogues, the catalogue holds a real and growing list. The galaxy is dense with worlds that nobody sees because nobody can. They emit too little light, and the only way to find them is to wait for them to drift across the line of sight of a more distant background star. Some named rogues, besides PSO J318, 5-22, include CFB-DSIR 2149-0403 OTS-44, which has its own small disk of dust around it, suggesting it may even be in the process of forming a small system of moons, CHA 110-913-773-444, WISE 085 5-0714, which we met earlier, as the coldest characterized atmosphere, and SIMP J 0136566 3 plus 0 9 33473, with an unusually strong magnetic field. Each one is a soft variation on the same theme. A planet, drifting alone, doing what planets do, far enough from any star that no daylight reaches it. A different kind of solitude record belongs to the catalogue's loneliest wide-orbit planets, planets that have stars, but whose stars are very, very far away. The clearest example is HD 106906b, which orbits its binary host stars at a distance of about 738 astronomical units. From the planet's surface, the host stars would appear as a pair of bright stars in an otherwise dark sky, not as suns. The planet's year is more than 15,000 Earth years. It is thought to have been gravitationally scattered into its current orbit by an encounter with another massive body in the system long ago, and the orbit it now follows is the slow, long-period orbit of that scattering event. a possible analogue for what a true Planet 9 might look like in our own solar system. If the speculated outer solar system Planet 9 exists, it might sit on something like this kind of wide, slow, scattered orbit, far from the Sun, far from anything else, taking thousands or tens of thousands of years to complete a single orbit. We do not yet know whether Planet 9 is real. We do know that HD 106906b is real, and that other systems with similar wide orbit outliers have been catalogued. The architecture is possible. The galaxy makes these planets, sometimes. You can imagine that softly. A planet on the far edge of its own system, its suns visible only as two bright points among the night sky, doing what it has done for 15,000 years and what it will continue to do for 15,000 more. Solitude, not as tragedy, but as stillness. The wider rogue planet population is one of the catalogue's most actively debated mysteries. Most rogue detections come from microlensing surveys, looking toward the galactic bulge, where the stellar density is high enough that brief alignments between background and foreground objects happen often. Most rogues are detected as a single brief lensing event, with the host or absence of host inferred from the shape of the lensing light curve. The estimated populations vary widely, depending on assumptions. Some surveys suggest a rogue population only a fraction of the bound planet population. Others suggest several rogues per main sequence star, meaning rogues could be the single largest population of planet mass objects in the galaxy. The implications, held softly, are that the galaxy is significantly more populated than the visible light night sky suggests. Below the limit of what we can directly see, drifting between the named stars, there are billions or possibly tens of billions of small worlds, most of them never to be detected, most of them never to be named. The rogue population is one of the catalogue's larger silences, a population that almost certainly exists, but that we can only catch in glimpses. Within the rogue catalogue, there is also a small subcategory of objects with their own moons or sub-companions. OTS 44, mentioned earlier, has its own dust disk around it, suggesting it may even be forming a small moon system. SIMP J01365663 plus 0933473, another rogue, has a strong magnetic field, strong enough that, if it had any moons, those moons would experience their own auroral displays. The wider population of rogue planets may well include systems within systems, small moon arrangements held by gravity around their parent rogues, doing what tiny systems do far from any star. The catalogue has not yet named any such moon systems, but the possibility is there. Some planets in the catalogue were not born around the stars they now orbit. Some were once part of other systems. Some have survived the deaths of their parent stars. Some orbit the corpses of stars rather than living ones. The pulsar planets, PSRB 1257 plus 12, B, C, and D, were discussed earlier in the records of cold. They are the first confirmed exoplanets in history, and they orbit a neutron star, the remnant of an ancient supernova. Their existence proves that planets can either survive the death of their parent star or form anew from the debris afterward. A different kind of survival record belongs to WD 1856 plus 534, B, a Jupiter-sized planet that transits a white dwarf about 80 light-years away. The planet's year lasts about 34 hours. The white dwarf is small, about the size of Earth, and faint, but the planet is large enough that its transit produces a clear, deep dip in the white dwarf's light. The configuration is extraordinary. The white dwarf is the burned-out core of a star that long ago expanded into a red giant, swelled outward to many times its original size. and then shed its outer layers as a planetary nebula before collapsing back down into the small, dense white dwarf state. Any planet in a close orbit before that expansion should have been engulfed and destroyed. WD 1856 plus 534b was not. Either the planet migrated inward to its current orbit after the white dwarf had finished cooling, or it somehow survived the red giant phase in its original location. Either explanation is unusual. The world is, in any case, alive. It still orbits its dead sun. The catalogue holds it as proof that planets can outlive their stars. A different kind of origin record belongs to the planets that show signs of having been gravitationally scattered out of one orbit and into another. HD 80606b is the clearest case. Its orbit takes it from a distance of less than 1/10 of an astronomical unit at periastron, closer to its Sun than Mercury is, to ours, out to nearly an astronomical unit at a pastron. Its eccentricity is about 0.93. During the close approach, the planet's atmosphere is heated rapidly and stretched outward. During the long, slow drift outward afterward, the atmosphere cools. The planet experiences, every one of its 111 Earth days, a single, intense heating event, followed by a slow recovery. Astronomers can watch this happen in real time, across multiple orbits, using the planet as a natural laboratory for understanding what hot Jupiters look like during their close passes. The planet is believed to have been scattered into its eccentric orbit by another world that was itself ejected from the system long ago. The current orbit is the long faded fingerprint of an ancient collision. Another quiet category of records, the exomoons. Moons, orbiting exoplanets, what astronomers call exomoons, are extraordinarily difficult to detect. The signal a moon produces during a transit is much smaller than the signal of the planet itself, and the moon's position relative to its host planet changes from transit to transit. The leading candidates remain unconfirmed. The most prominent is the candidate moon around Kepler, 1625b, a Jupiter-like planet in a year-long orbit around a Sun-like star, where the candidate moon is roughly the size of Neptune. A second candidate, around Kepler, 1708b, is similar in nature. If confirmed, these would be the first known moons orbiting planets in another solar system. They would also be unusually large, much bigger than any moon in our own solar system. The catalogue holds these candidates softly. The signal is there, in the transit data. Whether the signal really represents a moon or a stellar artifact is still being debated. The possibility is real enough that the worlds may well exist. The certainty is not yet final. Some questions in the catalogue take decades to resolve. A different kind of strangeness record belongs to J1407b, a young planet whose host star, J1407, briefly dimmed and then brightened in a complex, slow pattern over several weeks, years ago. The pattern of dimming has been interpreted as the passage of an enormous ring system in front of the host star. If the interpretation is correct, J1407b has rings about 200 times the diameter of Saturn's large enough to extend roughly 90 million kilometers across, about half the size of Earth's orbit around the Sunday. Gaps in the dimming pattern have been interpreted as moons clearing lanes through the ring system. If the rings are real, J1407b is the first known ringed exoplanet, and it would be a young, dramatic, slowly decaying ring system, unlike anything in our own solar system. Some recent analyses have argued that the ring's interpretation may not hold up, that the dimming pattern could have other causes. The case is open. The world may have rings. The world may not. Either way, the catalogue holds a small, soft mystery, a young giant planet far away, with a strange and possibly enormous adornment, slowly turning around its sun. A different kind of vanishing record belongs to Fomalhaut b. This is the world that may have never been a world. It was first directly imaged about 2 decades ago as a bright moving spot in the dusty debris ring around the nearby star Fomalhaut. For a few years, it was held as one of the first directly imaged exoplanets. Then, over the following decade, the spot faded. It expanded. It moved differently than a real planet would. Current interpretations suggest that what was imaged was not a planet at all. It was the expanding debris cloud of a recent collision between 2 unseen smaller bodies. The cloud, slowly dispersing, has now faded below the detection limit. The planet no longer appears in observations. You can hold this softly. A world that may have never been a world. A small, slow puff of dust that briefly looked like the first directly imaged exoplanet. The catalogue is alive and changing. Sometimes a record is added. Sometimes a record turns out to be something else. The catalogue corrects itself, patiently, over years and decades. A few other candidate planets have similarly faded from the catalogue over time. Some early radial velocity detections, made before the technique was fully understood, have been reinterpreted as stellar activity rather than as planets. Some early transit signals have turned out to be eclipsing binaries, 2 stars passing in front of each other, rather than a planet passing in front of one. The catalogue is more reliable today than it was 20 years ago, but it still occasionally produces detections that are later withdrawn. Each withdrawal is a small, soft entry in the catalogue's history, a record holder that briefly held a record and then quietly stopped. Fomalhaut b is the most prominent example, but it is not the only one. The catalogue is alive in both directions, additions and subtractions, and over decades, it slowly converges toward a more accurate picture of what is really out there. Finally, among the records of strangeness, there are the planets with comet-like tails of escaping atmosphere. GJ 3470b, a warm Neptune about 100 light-years away, has a tail of escaping helium gas, trailing behind it as it orbits its star. The tail is visible in narrow infrared wavelengths where helium absorbs light, and it stretches out behind the planet for tens of thousands of miles. WASP 69b has an even longer helium tail, extending more than 7 planetary radii behind the planet. Hundreds of thousands of miles of slowly streaming gas, falling away into space. The mass loss is steady, but slow. The planets are not in immediate danger of disappearing. Over billions of years, their atmospheres may be entirely stripped away. The catalogue holds them softly, planets with long, faint trails behind them, breathing slowly outward into the dark. A few additional named oddities live softly at the edges of the catalogue. HAT P 7b, on its retrograde polar orbit, may also be one of the planets where corundum, the mineral that makes rubies and sapphires, condenses high in the atmosphere and falls back as a kind of precious mineral rain. The interpretation rests on theoretical predictions of how an atmosphere at that temperature should behave, more than on direct observation, but the prediction is consistent with what we see. Other ultra-hot Jupiters in the catalogue may have similar mineral rains, quartz, silica, or titanium oxide clouds in different proportions, all of them slowly cycling between the day side and the night side. The disintegrating planet category, briefly noted in the architecture records, deserves a second mention here under strangeness. KIC 1255754 8b, also called the vanishing planet, before later observations confirmed the slow nature of its evaporation, was the first ultra-short period planet observed to be actively losing mass to a comet-like tail. Its trail of vapor and dust extends in a narrow stream behind it, and the trail is so significant that the planet's transits look distinctly comet-like in shape, with sharp leading edges and slow trailing recoveries. Each transit is a small, visible signature of a planet slowly fading away. You can hold all of these softly. Glass rain, iron rain, ruby rain maybe, helium tails, comet tails of vaporized rock, slow dispersing debris clouds where a planet may never have been. The catalogue has more weathers than the solar system has worlds. The variety is the point. Drawn together, all of these records sketch a softly coherent picture. The galaxy contains many more planets than stars, possibly several times as many. Earth-sized rocky worlds are common, possibly the most common kind of planet in the galaxy. Hot Jupiters are rare, but visible. The intermediate planets, super-Earths, and mini-Neptunes, neither of which exist in our own solar system, are the most numerous detected class. Planets formed in the early universe still exist. Planets are still being born today in the disks of nearby young stars. Some planets orbit corpses of stars. Some planets orbit no stars at all. The catalogue is a long, patient list of variations on a small set of physical rules. The records themselves are not the most important thing about the catalogue. They are how the catalogue makes its limits visible. A planet hot enough to be a small star tells us how much heat a giant atmosphere can absorb before its molecules dissociate. A planet less dense than cork tells us how strong stellar irradiation can be at the right distance. A planet with no sun in its sky tells us how easily a world can be ejected from a young system. A planet older than the Milky Way's disk tells us how long planet formation has been running in the galaxy. The records are not exceptions. They are the limits of what nature allows. What you have walked through tonight, very softly, is the visible edge of a much larger story. For every record holder, there are thousands of less extreme worlds doing the same thing more quietly. For every named planet, there are unnamed ones still waiting in the catalogue of candidates. For every observation, there are years of patient watching behind it. The catalogue grows slowly. Each year, a few more records change hands. The hottest known planet of today may not be the hottest known planet of next year. The coldest may shift. The farthest may move further out. The catalogue is alive, and the universe is patient. And the work of finding all of this happens slowly, in small dips in starlight. What the records cannot quite show, even gathered all together, is how much of the catalogue is implied by them. For every extreme planet, there are hundreds or thousands of less extreme ones doing similar work more quietly. For every hot Jupiter, there are smaller, cooler giants. For every super-Earth on a 7-hour orbit, there are super-Earths on 100-day orbits and 1,000-day orbits, settled into stable patterns that the catalogue has not yet entirely mapped. For every record holder you have heard tonight, there is a wider population of soft variations around it. The galaxy, in this sense, is full of unremarkable planets. Most worlds are not extreme. Most are quietly average, somewhere between a super-Earth and a mini-Neptune, on a year of a few weeks or months, around a small dim red dwarf star, with a thin atmosphere and a tidally locked orientation. The records draw the edges of what is possible, but the great middle of the catalogue is gentler and more uniform. The strangeness sits at the outside, the ordinary fills the inside. You can think of the catalogue, if it helps, as a slow museum that no visitor will ever fully walk through. There are halls of hot worlds, halls of cold worlds, halls of small worlds, halls of large worlds. Each hall has a few extreme exhibits and a long stretch of ordinary cases. Each year, new exhibits arrive softly, and a few old ones are gently relabeled or withdrawn. The museum has no closing time. The galaxy keeps building new wings. We have only just begun to walk through the older parts. Behind every named planet, in every hall, there are countless unnamed worlds we have not yet found patient inhabitants of the catalogue, waiting to be noticed. What the records do not show, even when laid out one after another, is the deep stillness that holds all of them together. Each of these planets, no matter how extreme, is bound by the same quiet laws, the same gravity that holds you in your bed, the same pressure-temperature chemistry that makes weather on Earth, the same conservation of momentum that keeps the planets in our own sky on their familiar paths. The strangest world we have found is not stranger than the laws. The laws were always allowed to make it. The galaxy simply had the time and the room and the patience to assemble all of these arrangements out of the same atoms, and so it did. That ordinary population is its own kind of comfort. It means that the galaxy is not a museum of impossibilities. It is, mostly, a quiet field of small worlds doing ordinary planetary things, with a few dazzlingly strange ones scattered through it for the catalogue to find. We live on one of the gentler ones. Earth is not on any of the records we have visited tonight. It is not the hottest, the coldest, the oldest, the youngest, the densest, the largest, the smallest, or the strangest. It is somewhere in the middle, a small rocky world with a moderate atmosphere, in a moderate orbit, around a moderate star. The records we have walked through are how the catalogue shows us what we are not, which in turn shows us, gently, what we are. The closing thought is gentle. Every one of these records is, in some quiet way, a place. A real world. A real arrangement of atoms held together by gravity, somewhere out there in the dark. None of them have been visited. None of them have visited us. They turn around their suns, or drift through space alone, doing what they have always done, and we know about them only because someone, somewhere, looked patiently enough at the right small dip in light. The galaxy is roomy. The records are quiet. The universe carries its strangest creations softly, far enough away that they cannot disturb anything. The hottest world ever found is 650 light-years away. The coldest is 20,000. The oldest is 12.5 billion years old, in a small, dense globular cluster. The closest is just 4.25 light-years away, a number small enough that the light leaving it now would arrive while a child grew up. You can let all of these worlds settle gently into the dark behind your eyes. There is nothing you need to do with them. They are simply there, turning patiently, doing what they have done for billions of years and what they will continue to do for billions more. If you are still awake, you can imagine one of them, any of them softly. Pick a record. The hottest, perhaps, with its glowing metal vapor and its slow trailing tail of evaporated gas. Or the coldest, 20,000 light-years away, in a single brief alignment of light, never to repeat. Or Methuselah, in its dense globular cluster, with the ancient stars above it brighter than the dimmest constellations from Earth. Or the youngest planets, still gathering material from their disks, growing visibly under their patient observers. Or the loneliest wide-orbit world, 15,000 years per orbit, with its host stars appearing as two bright points among the night sky. Each of these is real. Each of these is doing what it does right now, while you are listening. None of it requires anything from you. None of it asks to be noticed. The galaxy holds them softly, as it has held them for billions of years, and as it will continue to hold them for billions more. Turning, drifting, glowing, cooling, all of it quiet, all of it far enough away that nothing can disturb you. And so we leave the catalogue where we found it, turning softly in the dark, full of small, impossible worlds we will never visit, each one held safely behind hundreds or thousands of light years of quiet. The galaxy keeps making them and forgetting them and making them again while we sleep. Let your shoulders soften. Let the day grow distant. Let your breathing slow into the same long quiet the universe has been holding for billions of years. Sleep well, and good night.